So let's begin by doing a little bit of review of Raleigh's theorem. Recall that we said that if a function meets what conditions were there?
It's continuous on A to B, on a closed loop, and it is differentiable on the loop.
Now, here was an interesting question that came up in the other class related to these conditions. Oh, sorry, we should do our conclusion first to tie this up. So if our function meets these conditions, then what conclusion can I draw? We usually use the symbol C somewhere between A and B, such that not f of c, but f prime of c is equal to 0. That's exactly it. Okay. There is a c such that f prime is equal to 0. In other words, Raleigh's theorem is a horizontal tangent guaranteer, or guarantor. If the conditions are met, guarantees a horizontal tangent. Okay. Now, one of the questions that came up in class is this. What if we know that f of 1 is equal to 6, and f of 4 is equal to 6, and we know that f is differentiable on the interval 1 to 4. These three things. Does Raleigh apply? Now, before we answer too quickly, let's consider what these implications are. First of all, do we meet the first condition that f of 1 equals f of 3? Yes. Next question. Do we meet the condition that f is continuous on the closed interval 1 to 4? Yes, because f is differentiable on the closed interval 1 to 4, and differentiability implies continuity. If f has a tangent line at x equals c, it must be differentiable at x equals c. So although it does not explicitly state it, it gives us enough information to infer that f is continuous on 1 to 4 because it is differentiable. Next question. Is f differentiable on the open interval 1 to 4? If we consider the set that we're talking about, what we know is that f is differentiable for every value from 1 to 4, including 1 and 4. Does that include the open interval, 1 to 4? It does. And therefore, f is differentiable on every value from 1 to 4 because the open interval 1 to 4, here's a math symbol for you, is a subset of the closed interval 1 to 4 is included in it. Yes?
So when we say that if that is differentiable in some interval,
on that same interval. Yeah, exactly. Because differentiability implies continuity on all theorems. So it turns out that just knowing these two pieces of information, here and here, are enough to guarantee that Raleigh applies. Does that make sense to everybody? Okay, good. Any questions on that? We can. Do you have any questions on the homework?
Number 6.
Number 6. Okay.
what if
The opposite.
Like, if f is continuous on that interval, then f
Oh, is not necessarily differentiable, no. Continuity does not imply differentiability. And a good example of that is f of x equals the absolute value of x on negative 1 to 1. Continuous.
all x is equal to 0.
Yeah, we have a sharp corner at 0. So continuous but not differentiable. Good. Okay. So, number 6. What is the function and the interval that we're talking about?
1 minus x squared, square root of 1 minus x.
Ah, okay. On the interval negative 1 to 1? Okay. So first, let's look at a graph so we can understand what we're talking about. And when we look at a graph of f, we can see right here, pretty obvious that it is continuous on negative 1 to 1, and it's also clear that f of negative 1 and f of 1 are both 0. What about differentiable? Well, to find out, let's take a derivative and just ask, does this derivative have values for every x on the open interval negative 1 to 1? And if we take the derivative, we get f prime of x equals negative x over root 1 minus x squared. Okay. Now, is this function valid on every x in the open interval negative 1 to 1? No? What x is it not valid for? That's not in that interval. X equals negative 1 is not in the open interval negative 1 to 1. And neither is x equals 1. So my function has vertical tangents at the endpoints. That's okay. It is differentiable on the open interval negative 1 to 1, but not the closed interval. But I don't care.
Because close.
Ah, so Jason's having trouble interpreting the question. Got it. So, when we consider a function on the closed interval and we ask, does Raleigh's theorem apply, then we have to check the 3 conditions for Raleigh's theorem. Does f of a equal f of b? Check. Is f continuous on the closed interval? Check. Is f differentiable on the open interval?
Always continuous.
Always open.
Oh, because it's at the endpoint.
Right. We are allowed to be not differentiable at the endpoints. Exactly. And so since it meets these 3 conditions, therefore Raleigh's theorem applies. And it's pretty obvious that the c that we're looking for is going to be 0. That's going to be the point where f prime is equal to 0. So this was a slippery one. This one just barely met the conditions, but it did. And there are other functions out there that are like this. Okay? Good. All right. What we'd like to do here is to start relating average rates of change to instantaneous rates of change. And as a warm-up to this, I'd like to consider f of x equals the square root of x. And I would like for you to find the average rate of change of f on the interval 1 to 4. Go. And you should have labeled your average rate of change either as delta f minus delta x or as f of 1 minus f of 4 over 4 minus 1. Did you do one of those two things? And that gives us 2 minus 1 over 4 minus 1, which is 1. Okay, so that's all nice. What does this mean? Well, if we take a look at a graph, maybe a smaller graph right here. Shrink this down a little bit. So here comes y equals square root of x. And what we just found was that the slope of the line that connects these 2 points right here is equal to 1/3. And do you guys remember what we call this line that connects 2 points on a curve? Secant line, exactly so. So this is the slope of the secant line. Now, here's the way that I want to think about this. This is the average rate of change of f. And so I start thinking to myself, so could it be the case that the instantaneous rate of change, somewhere between 1 and 4, is also equal to 1/3? In other words, could I draw myself a line that is tangent to the curve at some point in here so that the slope of the tangent line was 1/3 as well? Visually, it looks like I can. No? Jason's not satisfied. Right. So I have a single point of tangency right here. And right at this point of tangency, I draw myself a tangent line. And it looks like I can draw one so that the slope is 1/3 as well. And the reason I can do, one way to think about this, the reason I can do this, is that my slope is greater than 1/3 here and less than 1/3 here, so somewhere in between it ought to be 1/3. That's my essential intuitive reason for that. So is that a real thing? Did I discover a mathematical property, or was it just an accident? It turns out it's not an accident at all. It is in fact the mean value theorem. And to get at the mean value theorem and the conditions for it, I want to observe that the picture that we have here with my f, my secant line, my tangent line, if I were to simply take this point and pull it down to be level with f of 1 right here, I would be looking right at Raleigh's theorem. My tangent line would now be horizontal. So, I'm inspired to think that maybe, just maybe, if a function meets the conditions of Raleigh's theorem, except for f of a equals f of b, then I ought to be able to find a tangent line parallel to a secant line. So here it is. If f is continuous at the closed interval a to b, and it is differentiable on the open interval a to b. Notice no mention of f of a and f of b. Then there is a c somewhere between a and b such that f prime of c is equal to f of b minus f of a over b minus a. Now these two quantities here, f prime of c is the slope of the tangent line, and f of b minus f of a over b minus a is the secant slope. Yes.
So, instant this instantaneous slope of C
Uh-huh.
is equal to every slope of A to B.
Yes, let's clean up that language. The instantaneous slope of f at C is equal to the average slope of f over AB. AB. Okay. Now, before we see why it is true, I want to show you how this works out with regard to the function that we have right here. So we'll do this as an example. Clara, are you ready for an example? Okay. Okay. So in our example, notice we have a function and an interval. And we can check the conditions for the mean value theorem and then apply it if they work out. To check those conditions, I'm going to use the same kind of shortcut that I mentioned earlier. I'm just going to cut to the chase and find f prime. And I notice that f prime exists on every single number on the closed interval 1 to 4. Therefore, f is continuous on the closed interval 1 to 4, and of course, it is certainly differentiable on the open interval 1 to 4. So this is a frequent shortcut that I will take when I'm checking continuity and differentiability. I'll just check differentiability first. Therefore, I conclude that there is a C somewhere between 1 and 4, such that f prime of C is equal to f of 4 minus f of 1 over 4 minus 1. And since I already have f prime of x, I can simply replace x with c. And I've already computed that this is 1/3. Yes, sir.
Whatever C value is.
That's the c we're looking for. Yep. So I have this equation now. I can clear the fractions by multiplying both sides by 6 root c. And what I do, I get 3 equals 2 root c. Or c is the square of 3/2. And if we go back and look at our original graph right here, you can see that 9/4, which is 2 1/4, is a pretty close to the original point that I drew right there, where my tangent slope was equal to my secant slope. Yep.
Why do you have to find?
Ah, what good is it? Okay. In other words, what's the purpose here? Well, I'm going to invert my lesson a little bit then and explain a little bit about the use of the mean value theorem before I go off and prove it. Tomorrow, we're going to use the mean value theorem all day long to do stuff. But I'll give you just one idea of the use. About 20 years ago, am I really that old? Yep. About 20 years ago, a friend of mine from this area took a trip to Austria. And Austria, near Germany, fun place to visit, so on and so forth. She rented a little red sports car. And she actually spent some time driving up in Germany, which is a whole lot of fun, because in Germany they have the Autobahn. There is no speed limit. There you go. There you go. So she's driving in Austria, and she goes through a really long tunnel. Well, she's got a little red sports car. in a really long tunnel. What would you want to do? Of course, you would want to just open it up and see how fast you could go, which is exactly what she did. And about 2 weeks after she came back to the United States, she got a ticket in the mail from the Austrian government. No, there was a speed limit in the tunnel.
Oh.
And what they did was they had a camera at the beginning of the tunnel, and a camera at the end of the tunnel, and a timestamp on both cameras. And they went through and they looked for people that had gone through the tunnel at an average speed, total distance divided by total time, an average speed greater than the speed limit. And how did that help her? Well, because the position of her car is continuous, she can't teleport. And it is also differentiable. She has a speed at any given time, even if it's 0. Therefore, it satisfies the conditions of the mean value theorem. Therefore, since her average speed was greater than the speed limit, there had to have been at least one time when she was in the tunnel when she was going greater than the speed limit. It's mathematically certain. There's no way she can go before the judge and go, I know my average speed was too high, but I was never speeding. No, mathematically, she must have been speeding at least once. So she had to pay the ticket. By the way, she tried to ignore it, and they made the ticket higher.
Wow.
Told her the license would get revoked and stuff like that. So she paid it. No, she doesn't even need to know. They don't even need to know when she was speeding. Maybe she was speeding at the beginning, or maybe she was speeding at the end, or maybe she was speeding the whole way through. They don't need to know. All they need to know is that she was speeding once. So the beauty of the mean value theorem is it lets us to guarantee an instantaneous rate of change without ever having to find when it happens. And that's a really cool, powerful thing. It's the spirit of what we call in math existence theorems. I don't know what the answer is, but I know there's an answer in there somewhere. Okay, now let's get to the proof. The proof is going to be conceptually fairly simple, but there's a lot of detail. So I want you to understand the proof at a conceptual level, and also observe that the details are just saying what the concept is. And here's our concept. What I'm going to do is to start with a function that is well behaved. It's going to meet my conditions for being continuous and differentiable. Let me move B out a little bit, actually, so that we can see this more clearly. So here's A, here's B, and here's the secant line between them. What I'm going to do is I'm going to create a helper function that finds the distance between f and its secant line. A helper function that finds the distance between f and its secant line. And that helper function is going to be eligible for Raleigh's theorem. And I'm going to apply Raleigh's theorem to find a point where our helper function has a horizontal tangent. And that point will be the point C that I'm looking for. So let's go ahead and get these details out on the table. First of all, let y equal the equation of the secant line that connects these 2 points. Now, to get that equation, I need slope and point, right? So let me mark my 2 points. This point is a comma f of a. This point is b comma f of b. And the slope is the average rate of change that we know and love. And for my point, I can choose either a f of a or b f of b. No matter which point I choose, I'm going to get the same results. So that the equation for y, which is the secant line, is f of a plus f of b minus f of a over b minus a. times x minus a. Notice that this equation looks very intimidating, but it is just point slope form. Uh-huh. No, it's actually a secant line equation. And the difference between the tangent line and the secant line is the slope that I use right here. Yeah. Yes, that's right. Is the slope that you have. If I were using the tangent line for this entire thing right here, instead of my average rate of change, I would use f prime of a. Yep. Okay. Now we're going to create our helper function. We're going to let g of x be equal to the difference between f of x and y. In other words, what I'm doing is I'm computing the distance between those two. Now the reason I want to do this is this. Looking at the graph here, what can you tell me about g of a and g of b?
G of B.
Not so. G of b and g of a are actually both the same value. They are both 0. Because g is the difference between f of x and y. Right? And so since the secant line intersects the curve at a and b, the difference between them is 0. So that's the first point that I want you to observe, is that g of a and g of b are both 0. The second point that I want you to observe is that g is continuous on the interval a to b because it is the difference of two functions that are continuous on that closed interval a to b. F is continuous because that was our hypothesis. And y is continuous because it's a straight line. So g is continuous because f and y are continuous. And g is also differentiable on the open interval a to b because f and y are differentiable. And while we're thinking about g, let's actually draw a graph of g so we can see what it is. G of x is f minus y, right? So from here to here, g is going to be a positive value. And then from here to here, g is going to be a negative value, like that. So this is my graph of g. And it starts at 0 and ends at 0. And it's positive whenever f is above the secant line, and it's negative whenever f is below the secant line. So this is what g of x looks like. And it's pretty clear that it meets the conditions for Raleigh's theorem. Yes? 1, 2, 3. And therefore, there must be a c somewhere between a and b such that g prime of c is equal to 0. Going back up to here, on our graph we actually have two different points c, one there and one there. And you can see that if I go up and draw myself a tangent line, that tangent line here and here, both points are going to be parallel to the secant line. So what does it mean to say that g prime of c is equal to 0? Well, let's actually drill down into the details. Since g is f minus y, therefore we're saying f prime of c minus y prime is equal to 0. Or in other words, f prime of c is equal to y prime. But what is y prime? Y prime is the derivative of this big old line right here. And the derivative of any line is its slope, right? What is its slope? F of b minus f of a over b minus f. point at which our helper function has a slope of 0 is exactly the point where the original function f has a slope that is equal to the slope of the secant line, where the tangent line is parallel to the secant line. That's all I know. All right. You guys want to do a couple of examples? Sure. Let's do that. First of all, let's do some analytic stuff here. I want to take a look, first of all, at page 202, number 6. We have a function here, f of x equals ln of x minus 1 on the interval 2. And the question is, does the mean value theorem apply? And if so, find the C such that the conclusion MVT, very common mathematical abbreviation for mean value theorem. That's what, Claire, was that what you were where you went to? Yep. And it looks sort of like most valuable theorem, and that's actually kind of true. It's extremely useful.
Or there's we don't have to find
No, that's right. We don't have to check does f of a equal f of b. If it does happen that f of a equals f of b, what's the slope of my secant line? 0, in which case I set f prime of c equal to 0, and whose theorem have I just applied? Raleigh's theorem. So the mean value theorem includes Raleigh's theorem as a special case, which is nice. So we really only just need one. All right, so does it apply? Well, let's check continuity and differentiability in one step. What is f prime?
X minus 1 over
Other way, yeah. So 1 over x minus 1. Now, does this exist as a derivative on the entire interval 2 to 4? Yep. And because it exists on 2 to 4, therefore I can conclude that f is continuous on 2 to 4, and it is differentiable on the open interval 2 to 4. It's differentiable on the closed interval as well, but I don't need that as a condition for my theorem. Right. So I conclude that the mean value theorem applies. And to find that value of c, I'm going to set f prime of c equal to f of 4 minus f of 2 over 4 minus 2, which is the natural log of 4 minus the natural log of 2 all over 2. What is f prime of c equal to? It is equal to 1 over c minus 1. We can take the reciprocal of both sides and add 1 to both sides. And because the mean value theorem is so strong, I don't even really need to check that this value of c is in domain. It has to be. It's the only possible value of c, and MVT guaranteed me c. But if you are interested, as Tony is interested, you can actually compute it.
So we're calling A9. So we're calling A8 and 4.
Thank you. I was about to fuss at you about your decimal places. And you beat me to it. Good job. All right, and that is definitely between 2 and 4. So that's how this really goes here. Yes, ma'am.
So do we need to check like every time whether C is between the interval? As you just did.
Well, as I just said, because the mean value theorem has a guarantee, if I only have one option for a value of C, I'm not even going to bother to check. But sometimes the equation that you get here could have multiple possible values of C, and only some of them might be in domain. So there it is. Let's consider also number 8 on that same page. And here we have f of x equals inverse sine of x for -1 to 1 and x over 2 plus 1 to 1 to 3. Now when I look at a function that is defined in pieces like this, I need to check continuity and differentiability of the pieces, but I also need to check at the joint, where the two pieces come together at x equals 1. And I'm going to do those in a slightly different order than I did in the previous one. In the previous one, I could take the derivative and use the derivative to prove continuity, right? But when it comes to piecewise functions defined at the joint, I find that continuity is easier to check first. Okay? So let's start with just the pieces themselves. Let's consider y equals, or f of x equals sine x, so inverse sine x. And when I look at f of x equals inverse sine x on -1 to 1, then I find that inverse sine x is, you may or may not remember the graph of inverse sine, looks like so. It is continuous because sine is continuous, and it is differentiable except for the vertical tangents at x equals -1 and positive 1. So it is continuous on -1 to 1, and it is differentiable on -1 to 1, not including -1 to 1. That 1 worries me because that 1 is right in the middle of the interval that the question is asking about. In fact, just to be clear, the question here is asking about the interval -1 to 3. So I wonder about what happens at x equals 1 if the lack of differentiability in sine, inverse sine, could somehow be remedied. Turns out the answer is no, but let's get there. Meanwhile, I check the piece f of x equals x over 2 plus 1 on the interval 1 to 3, and that is obviously continuous and differentiable because it is a linear function. Check. But now I'm going to check at the joint where the two pieces come together. And to do that, I need to verify that the limit equals the function value. The function value is 1 over 2 plus 1, which is 3/2. To get the limit, I need to consider limits from left and right. And when I consider those limits from left and right, look at that, I get different values. I get pi over 2 for one of them, and 3 over 2 for the other.
So does that mean it's not continuous?
Exactly. Because these limits are different from left and right, I conclude that the limit overall does not exist, which means that f is not continuous at x equals 1, which is in the middle of my interval. That's enough to do the mean value theorem. MVT does not apply. Jason?
But also, type differential and x equals.
So here's what it looks like. Our function has a jump discontinuity, right, at x equals 1.
So it's not differentiable at x.
Yes, that's right. The derivative also fails to exist at x equals 1.
So if we want to check the derivative using the two-sided,
You would have to check f prime plus and f prime minus, that's right. Which would be a pain in the neck. If I wanted to go ahead and check derivative at 1, I would have to use the derivatives from left and right. F prime plus
Oh,
and
like
f prime
what
minus.
we do.
Yeah, using the limit definition. Okay, how are we doing? Now I want you to notice, just briefly, that here I took a different approach. I checked continuity at the joint first, whereas back here with this one, I checked the derivative differentiability first because the differentiability gave me continuity automatically. What's the strategy? The strategy is to use the most efficient method to get the information that you want. So if finding the derivative first is easy, do that. And if checking continuity first is easier, do that. Because in the case of our second function, finding the derivative at 1 would have required a lot of work. We would have required setting up two different difference quotients and taking the limits. Does that make sense to everybody? So do the easy thing first. I will see you guys tomorrow, and we will use the mean